Okay, today we will take a look at composition methods. And I normally don't use prepared slides. I like to just write on my Etch-a-Sketch or whatever you call that thing, the tablet. And but Dr. Tsang has created some really good notes on the topic. I would say better than my own notes, so I'm going to go ahead and use his notes and cover this topic because they're really good. So these are posted on CCLE, and you can download and follow along, or you can just kind of watch, and I'll try to explain as we go. Okay, so far we're still in the section where we are talking about how do we generate numbers from random distributions, right? How do we get random numbers from some probability distribution, and we're working with just the assumption that our computer is able to generate random uniform only, okay? And if we can start with random uniform, can we then get random other things? Okay, and so we've covered the inverse CDF method. Okay, you take the CDF, you invert it, and you can use that to generate random variables. We saw that the inverse CDF might not work if it's difficult to get the CDF, and so we had things like rejection sampling and whatnot to generate random variables, okay? And today we are going to look at what we call composition methods, okay? So composition methods use kind of these some mathematical tricks, or we basically compose the random variable by combining things that we know. So in the beginning, we will start with what's called well-known compositions, what we might consider well-known compositions. So these are using kind of the relationships that have been defined as, you know, how one random variable relates to other random variables. And so these are probably from Stats 100B, and you should have learned these. So things like if you have Z come from a random normal distribution, then the distribution of Z squared, okay, Z squared, if we say V is equal to whatever this random normal variable is, and you square it, then the result will be a chi-squared distribution, right? So you'll get a chi-squared distribution. If you have chi-squared distributions with m degrees of freedom, and we will talk about getting a chi-squared distribution with m degrees of freedom. Basically, you just take a sum of m chi-squared distributions with 1 degree of freedom. So if you have like five values of v and you add them up, then you will get a chi-squared distribution with 5 degrees of freedom, and so on and so forth. And if you have u coming from the chi-squared distribution with m degrees of freedom, and v coming from the chi-squared distribution with n degrees of freedom, and they are independent variables, then you get f, which is kind of the ratio of these random variables over their degrees of freedom, and you get the f distribution. Where do we see the f distribution appear? We see f appear in ANOVA, right? To calculate, what are we looking at? The f statistic is found by doing, I know a lot of you took 101B last quarter, so this should still be semi-fresh in your mind. So to get your f statistic, that's the ratio between what? MS, the source of your variation, divided by the mean squares residual or mean squares errors, right? So you take, you do the sum of squares divided by the degrees of freedom to get your mean squares, and you compare the variation that we see, the sum of squares that we see due to one variable, one categorical variable, versus the sum of squares that could not be explained, right? And Fisher said this thing is going to follow this distribution, and he named it F. Well, I don't know if he named it, but the F comes from the name Fisher, right? So Ron Fisher, we thank for statistics. Okay, and then you got the T distribution. T distribution's what? Sampling distribution of the sample mean when the variance of the population is unknown. Okay, and that's because in that case you're using the standard deviation of your sample as an estimate for the population variance or population standard deviation, and that introduces extra uncertainty. So we increase kind of the size of our tails here. All right, so that's what we have, and we're going to look at something called the Mueller Transform. So the Mueller Transform, this is a way to get some standard normal random variables by transforming uniform random variables. Okay, so how do we go from random uniform to random normal? This is one way to do it. Okay, if you guys have tried out your homework, we can get random normal, but you guys might have noticed that in order to generate one random normal variable, you need to generate 3 random uniforms, right? One random uniform to get your random exponential, another random uniform to decide whether to accept or reject that, and another random uniform to get the sign. Okay, so you need 3 random uniforms to get one random normal, all right? This one's a little bit more efficient in that you're going to use 2 random uniforms and you'll get 2 random normals. And there's no rejecting, so no samples get thrown out, no samples get rejected. So basically every single random uniform gets turned into a random normal. There's no rejection, and so this is a bit more efficient. In both cases, you're going to get standard normal you're going to get normal distribution, right? You're going to get a random normal distribution. The rejection sampling using the folded normal works perfectly. This Mueller Transform works perfectly, okay? It's actually, our computer doesn't even use this. This is a very good algorithm, but the computer uses the inverse CDF of the normal, which I've always been saying doesn't have a closed form solution, and that is correct. There is no closed form solution for the inverse CDF of the normal, but the computer just has a very good approximation, an approximation that's accurate to about 16 decimal places for the inverse CDF, and it uses that to get its random normal. So the computer is using inverse CDF with a highly accurate approximation of the CDF, and that's what the computer does. So as I was contemplating this lecture, part of me was wondering, is it worth covering this topic because we don't use it in practice, the computer doesn't use it, and we don't really generate random normal numbers by hand either. I think there's merit in it, in kind of learning some of these things and learning the idea of a composition and transform method. And so we'll cover it, and it's almost like a classic example of this kind of composition methods, or doing some transforms of our variables to get random numbers. And so almost every Monte Carlo textbook you pick up will at least have one section on the Mueller Transform, and it might just be like a few pages or like one paragraph or something, but it will be covered, and I think there is some merit to covering it, but I have to come with the caveat that it's not even what the computer does, okay? And I probably should look up how the computer calculates the approximation for the inverse CDF, but I actually don't know how it works. So We'll look at the Box-Mueller transform. And the idea behind the Box-Mueller transform is that we switch from Cartesian xy coordinates to polar coordinates, r and theta, okay? So I'm going to bring back some memories of multivariable calculus and change of variables and all of that. And we'll do that. Okay, some of you guys have trickled in late. There is an online poll going on, so make sure you see that and you respond to it so we get attendance here. And we'll say choose option B for the attendance here, okay? Again, don't tell your friends if about the online poll, because maybe I'll do a roll call and we'll see if everybody who responded to the poll actually is here. So, okay, so this is how we're going to do it. We're going to say x and y are random variables that are coming from the standard normal distribution. So x comes from standard normal, y comes from the standard normal. X and y are independent of each other. Okay, so because they are independent, if we want the joint distribution, all we have to do is multiply the PDF of x and the PDF of y, and we will get the PDF of the joint distribution x and y, okay? So for the standard normal, the PDF of x is 1 over root 2 pi e to the negative x squared over 2, and then the PDF for y is going to be 1 over root 2 pi e to the negative y squared over 2, okay? And I don't know if you guys have memorized the PDF of the standard normal yet, and if not, that's okay. All you have, the key part is if you see e to the negative x squared, it's going to look like the normal PDF, okay? Everything else is just kind of to make sure it integrates to 1. But if you see e to the a negative quadratic, then it's going to look like a normal curve. Okay, the other things are just so it normalizes to 1. Okay, and then so when we multiply these things together, we get 1 over 2 pi e to the negative x squared plus y squared over 2. So this is the joint PDF of x and y, which are both independent random variables. Okay. All right, and so what we are going to do is we are going to do a change of variables, okay? And so to go from x and y to polar coordinates, we say x is equal to r cos theta and y is equal to r sine theta, okay? So r being the radius from the origin, and then theta being the angle from, that goes from 0 to 2 pi, okay? And then so to do a change of coordinates, probably in your multivariable calculus class, you're used to seeing the change of coordinates in the context of integrals and things like that. And so for going from xy, you'd have a double integral, one going from covering some area, right? And so in this case, we might go from negative infinity to positive infinity for x and negative infinity to positive infinity for y. And then we would have a double integral here for r and theta. R goes from 0 to positive infinity, and theta would go from 0 to 2 pi. Okay, so the change of variables, we would have the double integral, and we would change kind of the area that's encompassed, but going kind of the range or the domains of r and theta are slightly different, but this is what we have. Okay. All right, so do you guys remember what happens next for the change of variables? Dx dy becomes what? R dr d theta, right? Okay, and that's, I don't know if you remember, the reason why is because you have the Jacobian, right? You take the ratio between the partial derivatives and all of this stuff, and so you get the Jacobian, and you have dx dr, dx d theta, dy dr, dy d theta, and you have the determinant of this thing. And then so, how does x change with respect to r? Well, if we say r is the only thing that's changing, and this is held constant, then x changes at a rate of cosine theta. How does x change with respect to theta? Then it becomes r times negative sine theta. And then, how does y change with respect to r, and how does y change with respect to theta? You have sine theta and r cos theta. And so when you take the determinant of that, you have r times cosine squared, okay, r cos squared of theta, and if you take and you subtract off this times this, then you get plus r sine squared theta, and our trig identity says this is going to be equal to r, and so when we kind of swap out, you know, the dx dy and all of that, we get r d theta, and effectively this becomes f of x and y times r, and the change of variables will go from this thing, so 1 over 2 pi e to the negative, and we can see x squared plus y squared is equal to r squared. That goes there, and then we multiply it by r. So this is the result that we get by doing our change of variables here. All right, is that okay? Bringing back good old memories from our multivariable calculus class. What is that? Is that 32? 32A? 32B. Okay, good times, right? All right, so we've got that. See, everything's useful. All right, so we have our, so after we do our change of variables, we have this, you know, our r d theta. And again, r is for positives, from 0 to positive infinity, and theta goes on the interval 0 to 2 pi, okay? And then we're going to do another change of variables. We're going to go from r to r squared. If it's easier or helpful, you can think of we're going from r to v, where v is equal to r squared, okay? And so if we say, you know, what is dv or what is dr squared, that's going to be 2r dr. Thus, this value r dr is going to be equal to 1/2 dr squared. Okay, so if we do another change of variables from r to r squared, we're going to get this. Okay, and this is what we have. So we're going to replace this thing, the r dr, with a 1/2 dr squared. Is that okay? You might be like, why are we doing this? Well, just go with it, all right? And so we have swapped out this thing, so we're changing it to r squared, and we're going to replace the r dr with a 1/2 dr squared. Okay, so we went from x and y to r and theta, and we're going from r to r squared, and this is what we end up having. Okay, so we have 1 over 2 pi e to the negative r squared over 2, and then 1 over 2, or 1/2 dr squared d theta. Okay, if we rearrange our terms, we now have 1/2 e to the negative r squared over 2 dr squared, and over here we have 1 over 2 pi d theta. Okay, all right. So here we just have a constant, 1 over 2 pi, and so we can say, we can kind of factor this as two independent distributions, and so 1 over 2 pi is a constant on the range 0 to 2 pi, and so that's equivalent to having theta drawn from the uniform distribution 0 to 2 pi. Okay, that's what we have here. This is the PDF of the uniform from 0 to 2 pi. Okay, and then if we look at this, if we think of r squared as just kind of like some value v, okay, then we have 1/2 e to the negative 1/2 times v, basically, okay? Or we, you know, and so this can be thought of as r squared itself is drawn from the exponential distribution with lambda equal to 1/2, okay? Because the PDF of the exponential is lambda e to the negative lambda times x, and if we just say x is r squared or whatever it is, then that's exactly what we have here. So this is the exponential distribution with lambda equal to 1/2. Right. Is this okay? So by doing a change of variables, we have successfully gone from x and y, which are coming from standard normal, to r and theta, okay, which are, or r squared and theta, which are coming from distributions that are easy for us to generate random values from. It's easy for us to get random values of theta from the uniform, and it's easy for us to get values from the exponential distribution by using inverse CDF. Okay, and then again, these are products of each other, so r and theta are independent, or r squared and theta are independent of each other, so we can just generate r squared at one point independent and generate theta independently, and then combine those two together, and we will get basically the joint distribution of r squared and theta, and then we can convert back to x and y, which are going to be in our standard normal here. So this is how the Box-Mueller transform works. We've got theta coming from the uniform distribution from 0 to 2 pi, and then we generate v coming from the exponential distribution with lambda equal to 1/2, where v is equal to r squared. Okay, and then we just say r is equal to the square root of v, which works because r is always positive from 0 to infinity. And then we will calculate x equal to, the random value r times cosine of the random value theta, and then y will be the random value r times the random value of sine of theta. Okay, and thus x and y will be coming from the standard normal distribution if we do this transformation. Okay, and to get values from the random exponential, we'll just use inverse CDF method. So we get doing this, the inverse CDF, if we say, is going to be negative 2 times the log of u coming from 0 to 1. This is the inverse CDF. This will come from the exponential with lambda equal to 1/2. Okay, so these things are easy for us, and by doing kind of this clever change of variables, we can now get values from the standard normal. Okay, Wikipedia has a nice little picture of this. Okay, has everyone responded to the poll? I'm going to go ahead and close this. Okay. All right, and then so let me do Box-Mueller transform on Wikipedia. We got this nice little picture here. Okay, so the along the radius, it kind of represents the inverse exponential, or not the inverse, but the exponential distribution, trying to express that values near the center are more common, and as we go further out from the radius, or further out from the origin, they become more and more sparse, whereas every angle between 0 and 2 pi are equally likely, and when you look at the resulting distribution along the x or along the y, it ends up looking like the normal distribution here. Okay, so all you have to do is you generate u from 0 to 2 pi, which is equivalent to getting u from 0 to 1 and multiplying it by 2 pi. And then to get the radius, you're going to get v from 0, 1 using the inverse CDF method. You do 2 log of that v, take the square root, get r. X is r cos theta, y is r sine theta. And we'll have normal values here. Okay. So with this, it's very easy to implement it in R code. Okay. So again, thank you to Dr. Tseng for writing all of this out. And so we have here we'll just generate 1,000 random values. And so we're going to say u is coming from r unif. Okay. Values of theta is going to be 2 times pi times u. And then we're going to get 1,000 values from r unif 0, 1 to get our v, and we calculate the radius based on that square root of negative 2 times log v, and then we do r times cos theta and r times sine theta. Okay, and so when we do that, this looks just like 2 independent normal distributions kind of spread out here. Does this look like 1,000 points to you? It doesn't look like it, right? But this is 1,000 points, right? Our eyes aren't very good at estimating crowds. You can try to count it, but there's 1,000 points, okay? Well, I don't know what, well, I'm assuming, but so you just plot the x and y, right? Okay. So so this is great. The box Mueller transform is an excellent method for getting values from the random uniform. I mean, not random, random normal. And you might ask, why doesn't R use this method? Okay. And the answer is we take it for granted, but calculating the log of a number is and the square root and cosine and sine, these are actually not easy operations for the computer. They actually require the computer to work hard. We're accustomed to just typing in a number into our calculator and pushing a button, and it instantly gives us a value. But it's not something that's easy to do. Like, if I asked you to take the square root of a number by hand, you wouldn't be able to do it, okay? We just say, you know, we know what a square root means conceptually, and that's good enough for us. We don't have to calculate the square root by hand, and we'll just use the calculator for it. Square roots by hand used to be taught in school back in the day, and then we just said calculators are better at this than we will ever be, so we're not going to teach it. And so nobody knows how to find a square root by hand, and that's probably fine. But we lose sight of, you know, when it comes to implementing things in the computer, we might forget that these operations, taking the log, taking the square root, taking the cosine and sine, these actually require the computer to work a little bit hard. And apparently, the inverse CDF that R uses, the approximation is apparently faster than whatever this is. So that's why the computer uses the approximating inverse CDF rather than this. But this was a rather clever solution for getting values from the random normal without having to throw away values in rejection sampling, which you guys will do and in your homework. Okay, are there any questions here before I move on? We're good? Okay, and then so now that we have values from random standard normal, okay, so we can get values from the standard normal, then it's relatively easy, or actually very easy, to go from standard normal to just any arbitrary normal, okay? Because all you have to do is you just multiply your random value z by theta and add it to mu, okay? So this is you probably had to do something like this in your Stats 10 class, right? You go from a measurement to your z-score, and then if you were given a percentile and you wanted to get back to the measurement, you first go to the percentile to the z, and then you go from the z to the measurement by doing mu plus theta times z, right? So that should be familiar. And you know, if you had a normal table, you know, your cumulative probability, your CDF table, you could generate random values of the normal, right? Just by doing inverse CDF method. So yeah, that would be like a good by hand exercise here. Okay, so W will end up being normally distributed with mean mu and variance sigma squared. Okay. Convolutions, this just means composing a new random variable by summing up other random variables, okay? So if you just say x1 through xm are independent random variables coming from some distribution, the convolution is going to be the sum of those things, okay? And so many random variables can be expressed as a convolution or expressed as a sum, okay? So the first one is the binomial, Okay, so the binomial, by definition, is the sum of independent Bernoullis. Okay, so you flip a coin, the Bernoulli, and but you do that m times, and then you say how many times did it end up heads, or how many times did it end up with a positive result, and that is going to be your binomial. Okay, so this is the definition of the binomial. The definition of the binomial is a convolution in that it's the sum of independent random variables. So in this case, so I know I'm having you guys generate binomial by doing inverse CDF in your homework, but if you wanted to, you could also generate binomial this way by using the definition of the binomial by saying, you know, generate u from 0 to 1, and if it's less than p, give it a value of 1. You do this m times, and then you add them up. Okay. Is that okay? And then there's all these other ones, right? So if you want a Poisson with mean parameter lambda, that can be expressed as the sum of other Poissons, okay? And so you know, we have this, and over here you have the negative binomial, which is a combination of a bunch of geometric things, and these are probably all things that you've forgotten, and that's okay. And inevitably someone asks, what do we need to know for the test? Which is always like the worst question you should be asking. But I would say you should definitely know the binomial, and you should know the chi-squared. Okay, the other ones probably you can look up at some point if you need to remember how they work. But I would say the chi-squared and the binomial you should know. So the chi-squared distribution with m degrees of freedom is just the sum of other chi-squared random variables with 1 degree of freedom. So you just generate m chi-squared variables with 1 degree of freedom, and the sum of those will be a chi-squared distribution with m degrees of freedom. Okay. All right, and the sum of a bunch of exponential distributions will give you the gamma distribution. So you have that. Okay, and then and you can use this. So if you have kind of basically the ratio, if you have two gamma distributions, okay. So gamma is a bunch of values coming from an exponential. If you have two gamma distributions and you take the ratio between u and u plus v, you're going to end up getting a beta distribution. Okay. And what is a beta distribution? It's the conjugate prior of the binomial distribution. If that means anything to you guys. Okay. So you know the beta and the binomial. So if the binomial distribution is what we use to see how many times the coin lands heads after m trials, then the beta distribution could be the distribution of possible values of that parameter p, which will vary from 0 to 1. Okay. Okay. We'll definitely do some Bayesian stuff in this class, and so we'll see the beta binomial relationship again. Okay, and then lastly, we've got mixtures of distributions. Okay, so can I just screen sketch here? All right, so you might have some normal distribution centered at 0 here. Okay, and then over here we've got a normal distribution centered at 1, 2, 1, 2, and 3. Okay, and then with 2 squared, so standard deviation of 2. So 1. So this will look like, that looks terrible. Man, it's hard. It's really hard to draw on a fairly vertical surface. Okay, so we've got, so this is normal 0, 1, and this over here is normal 2 squared, okay? And so the resulting distribution, when you combine those two, will look something like that, okay? Obviously better looking than that, but that's kind of the idea here, okay? So here we're looking at a mixture of distributions. So, and here we're going to say that each mixture occurs with equal probability. And so how can we draw a sample from this mixture? Okay, well, basically just use the definition of the mixture. You're going to have to do basically sample two variables. One, you'll use a uniform to decide which category or which mixture the variable is coming from. Is it coming from the standard normal 0, 1, or is it coming from the other normal 3, 2 squared, okay? And so basically you're going to just sample from the uniform 0 to 1, and if it's less than 0.5, it'll come from the first distribution. If it's greater than 0.5, it comes from the second distribution. And if you had a different mixing proportion, like it's 90% standard normal and 10% other normal, then you can just use the uniform there, okay? And the cutoff being 0.9 this time. And then once you've decided which mixture it's coming from, then you generate the actual value from that distribution, from that normal distribution, the 0, 1, the standard normal, or the other normal distribution. Okay? Does that make sense? So anyway, so here's just some math that says, yes, it is a proper PDF. And here, basically generate K from the probability mass function. And so you generate K from the uniform and do this accordingly. You can have many more categories than just 2. And it's the same idea. First generate U to decide which of the categories it's going to come from, and then generate the other value from that respective distribution. And you have a mixture of distributions. Okay? All right, is that okay? Are there any questions? Okay. All right, so good. I'm going to go ahead and do an actual roll call, and we'll do this. We'll read off a bunch of names. Okay.